Hello all, welcome back to ATM 5, Our Changing Atmosphere. In today's lecture, we'll be kicking off our discussion of water in the atmosphere. As with previous topics, we're going to lay some groundwork on this topic to understand the role water plays in the atmosphere. Then we're going to address questions related to how climate change affects and is affected by water in the Earth system. There are quite a few definitions in today's lecture, so make sure to review the terminology afterwards to make sure you understand these concepts. We'll be defining air parcel, absolute humidity, specific humidity, vapor pressure, dew point temperature, saturation vapor pressure, saturation specific humidity, and relative humidity. We'll be asking these questions. What are the different ways to measure water vapor content in the atmosphere? What are the conditions needed for condensation to occur? How do fog and dew form? And how will rising air temperatures under climate change impact water in the atmosphere? If you're interested in learning more about this subject, I highly suggest the free online course, Introduction to Tropical Meteorology, offered through UCAR MetEd. In particular, Chapter 5 of this course covers the distribution of moisture and precipitation. Before proceeding, let's review what we've covered so far. You'll recall that this is one of the most important figures in the course, as it depicts how energy moves through the coupled atmosphere-Earth system. In Lecture 5, we covered terrestrial and solar radiation. In Lecture 6, we discussed reflection of energy, which led to the concept of atmospheric and land surface albedo. In Lecture 6, we also covered how greenhouse gases impact the transfer of energy in the Earth system. In Lecture 8, we tackled aerosols, which can impact the pathways of energy by modifying atmospheric reflectivity. And in Lecture 9, we talked about how the ozone layer is important for absorbing high-energy solar radiation and preventing it from reaching the surface. In this lecture, and the following lecture, we'll talk about the distribution of moisture in the atmosphere, the processes under which clouds form, and about the transfer of energy via convection and condensation. As we discussed previously, water vapor absorbs radiation throughout the infrared and is consequently one of the most powerful greenhouse gases. Of course, water vapor is the gaseous form of water. When that water condenses to form liquid water, or when it forms solid water, that is, ice, it can change from having a warming effect on the planet to having a cooling effect. Clouds consist of cloud droplets, which are little balls of liquid or solid water suspended in the atmosphere. As is clear from the bright surfaces, clouds are highly reflective to both incoming and outgoing radiation. The Earth is the only planet in the solar system that maintains significant water in all three phases, as a vapor, liquid, and solid. The ocean, atmosphere, and land drive the cycling of water through these three phases, a process which is essential to life outside of the oceans. In the Earth system, water begins in the oceans, where warming drives evaporation from the ocean surface and into the atmosphere. Water vapor from the ocean is then carried inland by atmospheric weather patterns, eventually precipitating in either its liquid or solid phase. Water on the surface can form surface snow or ice, locking that water into natural reservoirs until warming causes them to melt. Liquid water rolls down the surface, pulled down by gravity, leading to both surface flow and underground flow. Plants can draw that groundwater from the land, locking it up temporarily until it is transpired back to the atmosphere. Eventually, that liquid water is carried back to the ocean, where it can again cycle through the system. Given the importance of water to our society and economy, it is no surprise that the water cycle is extensively studied. At UC Davis, Hyde 10, for instance, explores the extensive social, political, and economic issues around water. However, in this course, we're focusing on water in the atmosphere. To do so, we're going to need some basic tools. To understand the behavior of water in the air, we are going to focus on how a macroscopic package of air behaves as it's transported around the atmosphere. This package of air is called an air parcel and can be thought of as a balloon with an invisible and impermeable boundary. As the balloon of air is transported through the atmosphere, it can change shape, size, temperature, but the basic constituents of the balloon, like its mass or how many oxygen molecules it contains, stays constant. Within this air parcel, there are a couple of obvious ways of measuring how much water vapor is present. One way is to measure the total mass of water vapor and divide it by the volume of the parcel. This gives the water vapor density, also known as the absolute humidity. The units of absolute humidity are mass over volume, or in metric, kilograms per cubic meter. Another way is to measure the total mass of water and divide it by the total mass of air in the air parcel. This is known as the specific humidity and refers to the fraction of mass within an air parcel from water. The units of specific humidity are mass over mass, which is actually a ratio and doesn't really have any units. But sometimes we write it as grams of water divided by kilograms of air. Much like a balloon, as our air parcel floats around, its volume is maintained because of a balance between the molecules inside and the molecules outside. The force exerted by molecules bouncing against the inside of the balloon, trying to expand the balloon, is balanced by molecules bouncing off the outside of the balloon, trying to compress the balloon. This force per unit area is referred to as the pressure of the air parcel. When inward pushing and outward pushing forces are equal, the volume of the balloon stays constant. However, when the internal pressure is greater than the external pressure, the balloon will tend to expand, reducing its internal density and temperature, and thus reducing the internal pressure. Thus, the air parcel will stop expanding only when the internal force balances the external force. Similarly, if the external force is greater than the internal force, the balloon will be squeezed smaller, driving up the internal temperature and density, and thus the internal pressure. In both cases, the balloon will adjust to equilibrium with its environment. This notion of air pressure gives rise to another way of measuring water vapor content in a parcel, namely vapor pressure. By definition, the vapor pressure is simply the contribution of water vapor collisions to the total pressure exerted at the boundary of the air parcel. Its units are the same as pressure, force per unit area, or newtons per square meter. It is proportional to the absolute humidity, or water vapor density, times the temperature of the parcel. Recall early in the course we talked about how pressure varies as we move vertically through the atmosphere. Because gravity is pulling down the atmosphere towards the atmosphere becomes denser the closer we are to the surface. This tendency for the atmosphere to fall towards the surface is balanced by collisions with other air particles. As air becomes denser, it also bounces around and shakes more. These collisions mean that not all the air particles can actually fit at the surface. Nonetheless, the farther you get from the surface, the fewer air particles you'll actually find. As density decreases with altitude, so does pressure. In fact, both density and pressure decay exponentially fast with altitude. So what happens to our air parcel as it moves up and down? Well, at lower altitudes, the air parcel is subject to higher environmental pressure, more particles trying to squeeze its volume. This means the air parcel contracts, driving up the air parcel's density and temperature. On the other hand, at higher altitudes, the air parcel is subject to a lower environmental pressure, fewer particles trying to squeeze it smaller. Thus, the air parcel is free to expand, driving down the parcel's density and temperature. The observation that pressure and temperature increase and decrease together is a basic property of gas thermodynamics. The relevant principle here is Montan's law, discovered in the 1600s. This effect on parcels moving up and down actually explains why temperatures are also higher near the surface and colder at the top of the troposphere. Namely, the lower pressures higher up are associated with lower temperatures, whereas the higher pressures near the surface are associated with higher temperatures. These vertical changes in temperature in the troposphere have little to do with radiation, instead being driven by expansion and compression of air parcels. Okay, let's go back to absolute humidity and specific humidity. Recall, absolute humidity is the density of water vapor, and specific humidity is the ratio of water vapor mass to air mass. How do these two properties change as air parcels expand and contract? Well, if an air parcel moves up and doubles its volume, then its absolute humidity must halve. In this example, going from 10 grams per cubic meter to 5 grams per cubic meter. This is because the mass of water vapor in the air parcel is unchanging, but its volume does change. How about specific humidity? Well, both the mass of the air parcel and the mass of water vapor are unchanging, even as the volume changes. So the specific humidity actually stays constant regardless of how the air parcel moves. Thus, specific humidity is said to be conserved following the motion of the air parcel. Okay, now that we've laid some groundwork on how to describe water in the atmosphere, let's understand how air parcels saturate and give rise to clouds. Liquid water consists of big pools of water molecules vibrating in close contact with one another. Water vapor, on the other hand, are free water molecules that have escaped the confines of the liquid and are zipping around in the atmosphere. To allow a water molecule to escape the liquid, you just need to give it enough energy. The amount of energy needed per kilogram of water here referred to as the latent heat of evaporation. On the other hand, a water molecule returning to liquid from vapor will give that energy back to the liquid. Water at the liquid-atmosphere interface is continuously undergoing transition between liquid and gas, and vice versa. The amount of liquid is only kept constant because the rate at which molecules become gas is balanced by the rate at which molecules become liquid. If the container is open, water vapor will escape to the atmosphere and eventually evaporate completely unless extra water vapor is added to replace the escaping molecules. However, if we put a lid on top of the container, the system will tend towards equilibrium. Namely, the amount of liquid water and water vapor will balance each other so that the rate of creation of liquid and gas are equal. The air above the liquid in this case is saturated. You can think of this as the air having reached its maximum capacity for water vapor. If additional water vapor is added to the air, then the balance will be upset. The rate of water molecules becoming liquid will be greater than the rate of molecules becoming gas. Thus, the air will lose water vapor until that balance is returned. Up in the atmosphere, away from water at the surface, there is initially no liquid surface to maintain equilibrium. However, if temperatures become cold enough and individual water vapor molecules slow down enough, they can start sticking to other things in the atmosphere. These surfaces are referred to as condensation nuclei and include things like aerosols. The condensation nuclei provide a sticky surface for water to attach itself to, beginning the process of forming a liquid water droplet. As more and more water collects around these nuclei, liquid water droplets begin to form in the air. As long as the rate of condensation exceeds the rate of evaporation, these water droplets will continue to grow. In order for condensation to occur, we need plenty of water molecules and need them to be going slow enough for them to stick to nuclei and other water molecules. Since the speed of these water molecules is related to their temperature, the temperature of an air parcel plays an important role in controlling whether or not condensation will occur. Namely, cooler air enables more condensation than warmer air. This result is fairly intuitive. Faster water molecules are carrying too much energy to stay put. They will instead bounce off nuclei and other water molecules rather than sticking. Slower water molecules, on the other hand, are more likely to stick to nuclei and each other when a collision occurs. Since warmer air can hold more water vapor, we can actually trigger condensation by cooling down an air parcel, making water molecules move more slowly and making them more likely to stick together. The temperature at which condensation starts to occur is formally defined as the dew point temperature. When there is less water vapor in the air, lower temperatures are needed for there to be sufficient sticky collisions to trigger condensation. Thus, dew point temperature actually ends up being another way to measure how much water is in the atmosphere. Lower dew point temperatures are associated with lower water vapor content. Recall the vapor pressure is the pressure of air due to water vapor molecules. In fact, the vapor pressure determines whether or not the air will favor condensation or evaporation. Specifically, for a given temperature, there is a value of vapor pressure known as the saturation vapor pressure, above which condensation will be favored, and below which evaporation will be favored. Going back to our earlier example, if we have a container at saturation, then the vapor pressure is equal to the saturation vapor pressure. Adding more water to the air will increase the vapor pressure and so drive condensation of the water. The saturation vapor pressure is a function of temperature, governed by what is known as the Clausius-Clapeyron equation. In this chart, the x-axis represents temperature and the y-axis represents vapor pressure. As we go up the y-axis, we have more water vapor in the air. The gray region on this plot refers to air that is above saturation. That is, there is too much vapor present. If this state arises, water will quickly condense out, driving the vapor back towards saturation. So air parcels aren't observed in this regime in the real world. Air is either saturated or unsaturated. Since vapor pressure and temperature both drop with altitude, it can be difficult to determine at exactly what altitude condensation begins. However, because vapor pressure is intrinsically linked to the mass of water vapor in a container and its temperature, we can instead define a quantity known as the saturation-specific humidity. This quantity determines, as a function of temperature and pressure, the specific humidity needed for condensation to occur. Here we see three characteristic curves, which may be associated with saturation-specific humidity as a function of altitude for three different surface temperatures. As expected, saturation-specific humidity is smaller at lower temperatures. Namely, less water vapor is needed in the air parcel for saturation to occur. Also, saturation-specific humidity drops off rapidly as a function of altitude. So an air parcel that is unsaturated at the surface will quickly become saturated as it rises. We'll revisit this plot in the next lecture to understand the formation of clouds. Before we conclude for the day, we need to define one more quantity used in measuring moisture in the atmosphere. You've probably often heard of relative humidity, as it's commonly provided when humidity is reported in the weather. It is actually just a measure of how close we are to saturation, defined as the ratio of the specific humidity in the air to the saturation-specific humidity, and represented as a percentage. Thus, at 0% relative humidity, there is no moisture in the air. At 100% relative humidity, the air is completely saturated, and any drop in temperature or addition of water vapor will produce condensation. In fact, at 100% relative humidity, sweating of humans is not particularly effective because it's very difficult for that water to evaporate from our skin and into the air. Consequently, at 100% relative humidity, exercise can be dangerous because we are unable to cool ourselves down naturally through sweating. In between 0% relative humidity and 100% relative humidity, there is water vapor in the air, but the vapor phase is nonetheless favored. That is, liquid water, if it's available, will evaporate and drive up the amount of water vapor in the air. At 100% relative humidity, specific humidity equals saturation-specific humidity, or in other words, vapor pressure equals the saturation vapor pressure, or in other words, the air temperature equals the dew point temperature. Since saturation-specific humidity appears in the denominator of relative humidity and is closely related to temperature, relative humidity varies inversely with temperature. For a fixed amount of water vapor, relative humidity is low at higher atmospheric temperatures. Conversely, at lower atmospheric temperatures, relative humidity is high. This means that relative humidity is usually highest at the coldest time of day, typically right before dawn. This is also at the point when condensation is most likely to occur in the environment. This observation actually explains the formation of morning dew, or fog. Overnight radiative cooling by the land surface drives ground temperatures and near-surface air temperatures lower, and in turn drives up relative humidity. When relative humidity exceeds 100%, the water vapor will begin to condense to form water droplets, or fog droplets in this case. When the sun rises, it will warm the air and drive the evaporation of the fog droplets back into water vapor. Relative humidity is closely connected with dew point temperature. When relative humidity is 100%, the air temperature equals the dew point temperature, so any subsequent drop in temperatures will produce condensation. Temperatures farther above the dew point temperature are then associated with lower relative humidities. Okay, let's test our knowledge. Consider the example shown here. In a particular region, polar air may be completely saturated at -2 degrees Celsius, or 28 degrees Fahrenheit, meaning 100% relative humidity. By comparison, desert air may have 16% relative humidity at 35 degrees Celsius, or 95 degrees Fahrenheit, far from saturation. The dew point temperature of the polar air is -2 degrees Celsius, and the dew point of the desert is 5 degrees Celsius. Which location has more water vapor in the air? Although the desert will feel drier, after all, liquid will readily evaporate as the air is far from saturation, its dew point is higher than that of the polar air. Thus, there is actually more water vapor in the air than in the polar regions. Thinking about this another way, in the desert region, 100% relative humidity is achieved at a higher temperature, meaning there is more water vapor present to condense. So, if we were to cool the desert environment down to -2 degrees Celsius, we would actually be in the supersaturated regime and will have produced water droplets well beforehand when we have reached saturation. So what does this all mean in light of climate change? Well, we know that warmer water surface temperatures have more energy to evaporate, as, on average, water molecules are moving faster. Also, warmer air has a higher saturation-specific humidity, so warmer air is inherently able to hold more water vapor before condensation occurs. This increase is on the order of 7% per degree Celsius, in accordance with Clausius-Clapeyron. Thus, we can conclude that global warming will certainly increase the amount of water vapor in the atmosphere. This result has been independently verified through multiple observational datasets. We have seen an indisputable increase in the amount of water vapor in the atmosphere over the past several decades. As water vapor is a greenhouse gas, this has exacerbated our effect on global temperatures. Although the amount of water vapor in the atmosphere has been increasing, this does not necessarily translate into more precipitation. In fact, the consequences for precipitation are highly dependent on location. In areas where water is plentiful, for example over the ocean, this can drive up precipitation because relative humidity is largely unchanged, even while the air is holding more water. However, in areas where water is scarce, for example over the deserts, this can suppress precipitation because it is harder for the air temperature to reach the dew point temperature. Consequently, places like Northern California are expected to receive more precipitation in a warmer climate, whereas the deserts of the U.S. Southwest are expected to receive less. This is the basic underlying physical principle that gives rise to the rule of thumb in climate change: wet becomes wetter, dry becomes drier. Okay, certainly a lot of technical background today, but enough to lay the groundwork for our understanding of water in the atmosphere. We'll be continuing this thread next time as we discuss clouds and precipitation.